But you can imagine ancient man sitting on the earth, staring up at the heavens and wondering, what are these things in the sky? What is the sun? What are the stars? Now certainly these folks noticed that the stars seem to move across the heavens during the night, and certainly our closest star, the sun, definitely rises in the east every day, moves in a great big arc, settles in the west, and some 12 hours later seems to repeat that journey. So wondering about the stars and the sun, maybe a very natural question about them, beyond what they are, is how high are these things? How high is the sun? Now it would be nice if we could just climb up to the sun, drop down the rope back to Earth, and measure the length of that rope. But of course we can't do that. So to work out the height of the sun, we need to measure something other than the actual height. What can we measure? Well, it feels like we can't measure much at all. But the only thing I can really imagine myself doing is, here's the ground, I'm looking up at the sun. Perhaps the only thing I can actually measure is this angle of elevation. So I'm in a situation like this. Here I am, standing on the ground, looking up at the sun, and I can measure my actual angle of elevation to it. And that doesn't seem like much for me to go on to work out the height of that sun. But then the scholars of ancient India actually realized that is enough information to make some good headway to understanding the height of the sun. That if ever I've got an object moving in a great big arc, in fact, just to get the math simplified, they assumed the sun was moving in a circular arc, there's enough information, apparently, from just knowing that at that angle of elevation to say something about the height of that particular sun. Astounding. So the subject of circlometry was thus born. Now, I should warn you, circlometry is a word I use. I made up that word. But what I'm really doing here is studying the height of a star in circular motion, trying to work out the mathematics behind that. I'm calling it circlometry. This is the work of the ancient Indian scholars. All right, so they actually figured out a way to get some mathematics going on that picture right there. Well, what mathematics? Well, as I said, they had to make the first simplifying assumption we are really talking about circular motion. Fair enough, that seems like a good first approximation for the motion of the sun. They also made another starting, well, I can't call it an assumption. They decided to call the radius of this circle 1 unit. Now, there's one very big unit, some huge number of miles, but let's call that 1 unit. That way we can at least get the mathematics going. In fact, the Indian scholars realized if we ever one day figure out the exact radius of this circle, we could actually change all our mathematics with quite some ease and actually adjust all our calculations. So assuming the radius here was 1 wasn't too much of a problem. Just scale all the figures up by a factor of the correct radius once you know what the correct radius is. So the theory of circlometry was thus about trying to figure out the height of objects moving on a big circle of radius 1, one big unit. Right, this is a brand new topic. In fact, since they were inventing this topic, they could make up names for all the different features of the topic. So when you're first doing something new, you get to make up names for it. So the Indian scholars actually gave a name for the height of a star at different angles of elevation, x. And they called it the jya of the angle. Now, I'm in a bit of a pickle here because I'm trying to say a word that was written in Sanskrit in English. So the English version of that word was J-Y-A, jya. So if this angle, say, was 65 degrees, then they would say the jya of 65 degrees is whatever this height turns out to be, that actual length. Made up word, they're inventing this topic, they could call it whatever they like. Grand. So the Indian scholars actually figured out a set of mathematics to work out the jya of different angles. The jya of 1 degree, how high the star is when it's just above the horizon, 1 degree up from the horizon. The jya of, say, 45 degrees, and so on. Now, in the 10th century, mathematics took off in the Middle East, and all the Islamic scholars translated a lot of these ancient Indian texts from Sanskrit into Arabic. Now, they looked at this work on astronomy, the motion of stars, the motion of points in circles, and they copied all the words, all the texts from Sanskrit into Arabic, and they saw the word jya. Now, these Islamic scholars were very much aware this was a brand new word made up for this new mathematics, so they copied the letters, literally letter for letter, J-Y-A, into Arabic, which became known as jiba. Now, again, I'm having a problem. I'm trying to say in English words from Sanskrit being translated into Arabic. So I'm probably making a terrible mess of the actual names here, but the English equivalent is jiba, J-I-B-A. So, the height of the star at different angles became known as the jiba of x. For example, right now, if this really were 65 degrees, the jiba of 65 degrees is this height, whatever that length turns out to be. And then the Islamic scholars actually added to the mathematics of this theory, and they worked out more jibas of different angles, got this theory going even further. Then, mathematics took off in Western Europe around the 1200s. And all the Western European scholars went down to the Islamic world and copied texts, all the texts of different scholarly works, from Arabic into the scientific language of the time, which was Latin. Now, these Western European scholars went to Madrid, which was Islamic at the time, and copied these mathematics texts from Arabic to Latin. Here they made a curious mistake. It's lovely. They saw this word jiba in Arabic. They said, hang on, there's no word jiba in Arabic. There must be a mistake. Because it was very close to the actual Arabic word jaib, J-A-I-B. And jaib actually means cove or harbour, like a little inlet in a coastline, a safe place to put your boat at night, a harbour. And I thought, that's a funny thing. Why are they calling the height of the star at different angles the harbour of that angle? Odd. Nonetheless, they went with the word harbour, and they used the Latin word for harbour, which was sinus, which in English then became sine. So today, we use the word sine for the angle of, for the height of a star at a different angle of elevation. For example, if I say sine of 65 degrees, meaning this actual height here, whatever length that is, I mean that height. But I'm really saying the harbour of 65 degrees, which makes no sense. So there's a wonderful story of mistranslation here, that we're now going to be talking about the sine of different angles. So to us, the word sine in mathematics means the height of a point on a circle at a particular angle of elevation. So you can imagine, as you play with this theory of mathematics, which we'll describe today, of course, that after a while, you might become interested in other features of this diagram, not just the height of the star, but maybe its overness. How far left or right is it from you? So that length, the horizontal length on the bottom, that horizontal displacement, started getting a name as well. People called that the companion length to sine. It became known as cosine. So when I say, nowadays, the cosine and the sine of 65 degrees, I mean I'm standing on the ground, looking up at a star at an angle of elevation 65 degrees. When I say cosine, I'm saying it's that number of units displaced horizontally, and when I say sine, it's that many units displaced vertically. In other words, the height of the star. Sine and cosine are just the heights of stars at different positions along the circle.